All right. Good afternoon, everyone. Today we're going to be talking about soil electrical conductivity and especially soil apparent electrical conductivity. We're going to go first through a set of slides, and then we're going to do our exercise in R. So to go to our slides, you can find them in our website. It's going to be under today's date. So if you want to follow along on your side and take notes, you can do that. Otherwise, you can just follow on my side here. Okay, so soil apparent electroconductivity is the topic of today's class. My goals for us here are gonna be to discuss about apparent soil electroconductivity and what it is, discuss how it is measured, also discuss why this is such an important layer in precision ag, especially in row crop precision ag, or even any outdoors field level precision ag for that matter. And that's it. So to begin with, what is electrical conductivity? As the name implies, it is a measure of how much electrical current is conducted through a medium. And in our case, that medium is going to be mostly soil, but also the soil environment that's going to be composed of soil particles, of water, and air pores. And it's measured in either Siemens or millisiemens per meter. These are pretty common units for this type of measurement. So basically, this relates the level of ionic charges that are able to conduct electrical current. So imagine if you have a little glass with water and a little bit of salt, or if you have pure water, let's think about that for a second. If you just have pure water, there are no salts in there, electrical conductivity is zero because there is no salt to conduct that electrical current. As you start adding salts to water, and making a solution with water and salts, the more salts you add to water, the higher is going to be the electroconductivity of that mixture. And initially, this type of measurement and this type of technique of measuring electroconductivity was developed to measure salt concentrations in soil water and relate that back to crop growing suitability. So, for example, many fields around the world have issues of being saline or sodic soils. What that means is there are so many salts in those soils that they really hamper plant growth, plant establishment. And that's because the higher salt amount or concentration there is in soil, the tighter that salt holds on to water. So even though these soils may have water, but that water is really difficult for plant roots to take up because the water is being held so tightly by all the salts in the water that water just is not available for crops to take up. And these soils that have these very high concentrations of salts are called either saline or sodic, depending on what type of salts are more prevalent in those soil conditions. And so initially, this type of technique of measuring soil water electroconductivity was developed to understand these soils, these saline and sodic soils, and understand what is the concentration of salts in those soils that after which point really start becoming limiting for crop water uptake. So how has it been traditionally measuring soils? How has soil electroconductivity been traditionally measured in any type of soil? So basically, this is something that a person will have to go out and collect a soil sample, bring that soil sample to a laboratory, saturate with water, and then use the extractant of that solution, of that mixture, and measure electroconductivity between two electrodes. So imagine you bring a soil, you mix with water, you allow it for it to react for some time, you extract that soil, that water that is coming, that is in equilibrium with that soil water solution, you extract that, and then you just have two electrodes inserted in this soil water to then give you an idea of how much current is being conducted between the two electrodes, right? So one electrode emits electricity, the other one receives it, and the more salt there is in that water mixture, the more electricity will be transmitted from one electrode to the other. As you can imagine, doing this is very time consuming, right? So you have to go to a field, collect a soil sample, bring to a lab, do all these methods to really be able to measure soil electroconductivity. So it's really not something that initially was really thought of as a precision ag type of technology or measure. Then we have this concept here of bulk soil apparent electrical conductivity. And I guess the key thing here is understanding that is apparent. So it's not soil electroconductivity as is, it is soil apparent electrical conductivity and also relating to the bulk soil. So what does that mean to say that something is bulk soil apparent electrical conductivity? So this is basically a measure that is taken in situ and it's basically taken on the soil itself, out on the field. It's not something you would collect a sample and bring into a lab. You actually measure this electric conductivity of the bulk soil. And this includes both a liquid and a solid phase. So what we're seeing here is basically just a depiction of a soil profile, or not a profile, but a soil cut, where we see here three main pathways of soil bulk electrical conductivity, apparent electrical conductivity. So we have here the solid parts of the soil, which basically, is basically the mineralogy of the soil. So you have your soil particles being the solid phase. We have a liquid phase that may be interrelated with the soil particles. So it may be soil water that is in between soil particles, like we're seeing on where my mouse is. And then you also have a liquid phase that is related to soil particles, but it's not constrained by soil particles, which would be the second path here, where there is some airspace and that water soil liquid is basically at the interface between air pores and the solid soil particles. So when we're measuring soil bulk apparent electroconductivity, we're basically measuring how much electricity is being conducted through the solid phase. So going through, or the solid and liquid phase that are connected, including that liquid phase that is confined between those soil particles, and also how much electricity is being conducted by the purely liquid phase, which is this one here at the interface of soil solids and just air pores in the soil. And it is called bulk soil electroconductivity. Bulk comes from the fact that we're measuring electroconductivity across this different medium, as opposed to something that you collect a soil sample, bring to a lab, mix with water, and then only measure electroconductivity on the extractant of that solution. So only on the liquid phase. Here we're measuring electricity that is going through that liquid phase, but also through the liquid and solid interface as well. And that's why it's called bulk. All right, so then what are the methods that we have, especially in research, but also in commercial applications to measure soil apparent electroconductivity in situ or at the field without having to take a soil sample and bring to a lab? There are three main methods that exist for that purpose, and that includes electrical resistivity, electromagnetic induction, and time domain reflectometry. So these are things that you may have seen before, you may have used before if you're doing research in precision ag. And we're going to talk a little bit more in depth about each one of these three methods. So the first one here, electrical resistivity. A commercial example of this would be a Varius 3100 model, but basically any Varius model, any Varius equipment that measures electrical conductivity, it is using the concept of electrical resistivity. So how does that work? If you've ever seen a Varius rig being used or being pulled on behind a tractor on a field or behind an RTV on a field to assess soil electroconductivity, this would be kind of how that would look like from behind. So imagine that this is you looking forward with this equipment in front of you, and imagine that the tractor is further in front of this equipment and is dragging this equipment across the field. So what happens here is we have some internal electrodes like this one here that are emitting this electrical signal through the soil. And so this electrical signal is emitted, it travels through the soil, and it is sensed how much of that initial electrical signal that was transmitted, it sensed how much of that is being received by the outer parts of this. So here we're seeing kind of from the back, but if you were to look from the side, what here looks like a needle, this is not a needle, this is a disc. So there is a whole disc that we're looking at this direction of that disc, but if you were to look on the side, you would see the disc. So these are just discs that are in contact with the soil, and the inner discs here are emitting this electrical signal. That electrical signal is traveling through the soil, and how much it travels is going to depend on the electroconductivity of the soil, which we're going to talk a little bit more about what impacts that signal in a second. But that electrical signal travels through the soil, and then it is the signal that goes through the soil and reaches again another one of these discs is then sensed to get an idea of how much of that emitted electrical signal was received back by these different discs. And one thing that's really, really interesting about this technology is that you have some inner transmitting electrodes or discs, like this one here, that emits that electrical signal through the soil. And then the receiving electrodes, we have a couple different types here, or not types, but a couple of different distances away from the transmitting electrode. So we do have, for example, so this right here is a transmitting electrode. So it's transmitting that electrical signal. And this one right next to it is actually a receiving electrode, just like this one on the far left. The difference here is that the distance between the transmitting electrode, this one, to the receiving allows for, because there's a receiving here, there's also a receiving here. And you notice that the distance between the transmitting and the two receiving electrodes is different. So this receiving electrode that is closer to the transmitting electrode is going to give us soil electroconductivity at a shallow soil depth because it does not have as much space to travel. It travels on a shallow way and is already back to the receiving. Whereas the receiving electrode that's farther away from the transmitting one is going to give us an idea of deep soil electroconductivity. So the two closer ones give us an idea of shallow soil electroconductivity, and the two farther away ones give us an idea of deep soil electroconductivity. That's because since they are farther away from each other, the transmitting and the receiving on the left, that electrical signal has more soil volume to go through before it reaches back the receiving electrode, and therefore it gives us an idea of electroconductivity at a deeper layer. So normally, not all Varius equipment give you soil electroconductivity at two depths, but most commonly they will. So you would see data saying like soil EC at a shallow depth and soil EC at a deep depth. from this type of equipment because it gives you both of those depths because it has those receiving electrodes at different distances from the emitting one. And the same thing happens here on the right side of this diagram. I was just, I guess, telling you on one of the sides, but it applies to the right side as well. I guess before I leave this slide here, any questions about this? All right. So, and I guess, so how, perhaps I failed to mention this, but as this equipment is being dragged over a field, zigzagging over a field, collecting this data, it is also, it's collecting the data on the electrical, on electroresistivity and relating that to soil conductivity. And then it's also taking the GPS coordinates, right? So as it's moving across a field, it's taking the measurement and also taking the GPS to correlate or to know where in space that signal was when it was being run across a field. Yes, Tifton.
Is there a calibration procedure to do when using a Veris, or you just take for granted what is coming from the manufacturer?
So you can, so depending on the various equipment, there's going to be different sensors. So we're just talking here about the soil electroconductivity sensor, but there is also a optical sensor that provides you information on soil organic matter. And there's also a probe that collects soil and does a soil pH measure on the go as well. For the soil pH and for the optical sensor that is assessing soil organic matter, you can calibrate those. For soil electrical conductivity, if you wanted to calibrate, you could, but I don't think that's something that people do normally. Because for you to calibrate that, you have to come here and do all the hand sampling, which would be, extra work and cost. And also because of the reason that normally, although the actual value of electroconductivity can be important, but normally we're more interested in the relative differences in the field and not necessarily on the specific value that you're getting from it. And we're going to see that in some examples afterwards here that will help clarify. So from my experience, I don't think people really calibrate the soil electrical conductivity component of the Veris. But I could be mistaken. Perhaps some people do, but I'm not familiar with that.
Right.
Yeah, thanks, Marco. All right, so our second type here is electromagnetic induction. Well, perhaps before I move into this, let me just go back to the electroresistivity and just tell you that for this method to work, for electrical resistivity to work, those discs, that this transmitting and receiving discs, they have to be in contact with the soil, right? They have to be touching the soil. It almost looks like you're tilling the field, although it's not really tilling. You're just making a very slight cut that disc has to have to be in contact with soil while you're collecting soil electrical conductivity data with this technology. And I'm saying that because the next example, the electromagnetic induction, does not. So one of the commercial examples here is called Geonix EM38. There are some other as well. So what we're looking at here, imagine you're also looking at this implement from behind, right? So imagine that you're looking from this direction and there is a tractor or maybe an RTV in front of this equipment further down the road. So what we're seeing here is the way that this technology works is you have a transmitting coil and a receiving coil that they operate in a similar way as far as one of them transmits an electromagnetic signal and the other one receives how much of that signal is traveling through the soil and reaching the receiving coil. The difference here, though, is that it does not have to be in contact with soil. It can even normally it is very close to the soil or even in touch with the soil, but it does not need to be in contact with the soil, like the electrical resistivity example that we just saw before. And this is because it is operating on a principle of transmissivity of this electromagnetic signal. And so it is transmitting that electromagnetic signal that is traveling through the soil and is being received on the other coil. So this one here can also be dragged behind a tractor or an RTV, although it's not going to be cutting through the soil. There are no discs that cut through the soil like the previous one. This is just in very close contact, but maybe not fully cutting. I mean, it's not cutting through the soil. It doesn't even have to be fully touching the soil. Just a little bit above it is enough. One of the perhaps downsides of this is because it does not operate on that principle of the discs, then it only gives you information at one layer, at one soil layer. It's going, all that signal that is being, so that the electromagnetic signal is being transmitted through the transmitting coil, is traveling through the soil as one signal and then being received by the receiving coil, and you really don't get any information on what depth that is. So basically, one of the downsides, it is a fixed depth type of measure, and you don't have the flexibility to change that as you potentially could change that with electroresistivity, which was the previous example. These are two of the most common ones used in precision ag purposes for the reason that they can be dragged behind a tractor or an RTV, and therefore collecting data very fast on the go and just also taking that GPS coordinate as this moves through a field. So it's really, these are the two technologies that help us with precision ag, especially because you can do that in a very fast way. It is, simply, it's a simple way of collecting soil EC data without having to collect samples and send for a lab and so on. The third type here is called time domain reflectometry, or TDR. You may have heard of this when measuring soil water content. This also is used for that purpose. In the case of TDR, you basically have this equipment here with two rods, and these rods are inserted into the soil. One rod, again, emits a signal, the other one senses that signal. So it operates similarly from the perspective of one part of it is emitting the signal, the other one is receiving what travels through the soil and gets the receiving rod. However, this one is the least scalable one because you cannot drag this over the soil surface. You have to stop, take a measurement, press into the soil, take a measurement, pull it out, move to the next point, and so on. So even though this is one of the technologies that can be used to assess soil electric conductivity, it is the least scalable of these three. All right, so let's talk about what affects soil apparent electroconductivity. And this is going to come back to, I think, Marco's question as well. Well, before I show you, let me ask you all, I guess I just showed you the first one, but if you had to guess, what do you think would impact soil electrical conductivity?
Water content, bulk density.
Yes, water content, bulk density,
Salinity.
salinity of the soil. Say that again. Type of soil. What do you mean by that? Different textures, right? So different soil textures. Great. All those are great examples, right? So let's talk about some of those here, and let me show you what I had on my slide. So the main factors that affect soil electric conductivity are going to be soil salinity, right? So this was the reason why soil electric conductivity measurements were developed. Soil water content as well. Soil texture. And then things like soil temperature, organic matter, bulk density, and porosity are all impacting a measure that you get of soil apparent electroconductivity. However, the main three ones are salinity, water content, and texture. So I guess this comes back to your question, Marcos. So because soil electroconductivity, apparent electroconductivity, like we would measure in Precision Ag, is affected by so many factors, this data can really, I mean, the way that we normally use it is that we only interpret this data within the context of that field and not to really use to compare across different fields, right? So even the same field, so let's say you run a various equipment on a field today, and it was very dry. It was like you had a very long drought and you run it today. And then maybe you have some rain tomorrow, and after that water drains and you can enter the field again, you go and you measure again. You're probably going to get different values. Not because the soil changed, not because the salinity changed, but because the water content changed. So even comparing the same field on different dates could be troubling because, if I say, well, today my soil EC average was, I don't know, X, and in a couple of weeks, it's going to be X times 3. Is that because something that I really worry about changed, or is it just a matter of soil water content perhaps? Or maybe, if a field is grown with different crops, that could potentially impact as well some of these soil properties that in turn affect soil ECA measurements. So normally we use that soil electroconductivity data for that field relative to the values of that field, and we don't really compare much across. Especially because for us in precision agriculture, what is the main reason we use a soil EC rig, like Varis, for example? What are we trying to learn from that?
I think knowing the way iron is transmitted can show you how easily the fertilizer will be absorbed by plants.
Okay, that is true.
So can be the salt concentration of the soil, relative salt concentration,
So soil concentration of what?
salt concentration of the soil.
Okay. So all those are right. But the main reason why we use soil EC equipment in Precision Ag is because we are interested in relating that signal to soil texture. That is our main purpose in Precision Ag. Even so, let's say if you have a field that you're growing crops, so most likely there's no salinity problem, in a field that has been managed very similarly when it comes to irrigation, for example, or maybe crop type and how much a given crop type can require of water. So if everything else is similar across that field, we run a soil EC equipment because we want to relate that to soil texture. That is what we want. Meaning that if your field had, let's say if you irrigate half of the field and not the other half, and you recently irrigated and you go and do a soil EC map, you will most likely see an effect of the irrigated versus non-irrigated, which is not what we want, right? We are interested in the signal coming from soil texture. So for that to be true, the other factors have to be applied at a single similar level, right? For it to allow soil texture to control the signal of what we see on soil electroconductivity. So that's our main goal here. That's how this is used in Precision Ag in general. So let's see how a few of these factors affect soil electroconductivity. So before I show you some graphs here, let me ask you, how do you think that soil salinity and electroconductivity are related? Are they positively related, negatively related? What do you think?
Positive related.
positively, right? So as you increase soil salinity, you also increase soil electroconductivity. So this is a plot showing us a little bit of that relationship. So here we have apparent electroconductivity on the x-axis and solution salinity, or I guess, so ECE is basically the electroconductivity of the soil solution that you bring to a lab, bring the soil to a lab, mix with water, extract the water, and only measure the EC of the water solution. So that's what is on the y-axis. That would be the ground truth, right? So Marco was asking about ground truthing. That would be your ground truth. So here we have the ground truth data on the y-axis and the apparent electroconductivity on the x-axis. As we see, as you increase, let's see here in this case. So here in this plot, it's basically each one of these lines is relating to a different soil type. And these different soil types have a different concentration of salts. So what we're trying to show here is that for different soil types, regardless of the soil type, overall, as you increase your actual measured electroconductivity, you also increase your apparent electroconductivity. But that change depends on soil type. And again, this change in soil type in this case is related to soil salinity and how much salinity there was in those soils, but it could also be related to texture. And that's what we're mostly looking for. The other factor here is soil water content versus soil EC. So how do you think that they are related? What do you think, Polly?
I think they're positively related.
Right. So as you increase soil water content, you also increase electroconductivity, right? So let's look into that. So here on this plot, we have on the x-axis, we have soil volumetric water content. And on the y-axis, we have bulk soil conductivity, well, which is what we're talking about in Siemens per meter. And then each one of these lines is a solution with different salinity levels, going from 0.11 to 2.25. So a couple of things we can see here is overall, looking at the x-axis, as soil water content increases, apparent soil electrical conductivity also increases. And we're also seeing here for these different lines that represent different soil salinity levels is that as you increase your salinity level from the bottom to the top of this graph, you're also increasing your apparent soil electroconductivity. So soil water, the higher the water content, the greater it is electroconductivity and also salinity, right? So we're seeing that interaction of those two factors here. And then again, coming to the point that this is important to know because normally I'm not running a Varis rig to know about soil water content. I'm not running a soil rig to know about salinity levels. I am running it because I'm interested in understanding the relationship of soil EC with soil texture, which for us, so for us, when I say yes, I say those of us not working in saline or sodic soils, which I guess is all of us here in this class. If you're not working in sodic or saline soils, and then EC is not being connected to soil salinity to the extent of limiting plant growth, then in our case, our interest is to connect soil EC with texture. So knowing that is important, again, because if knowing what other factors also impact soil ECA can help us to think and plan better when going out and collecting soil EC to relate to texture. Because if any of these other factors are playing a role, they would be playing a role in the signal that you get and are going to dilute the signal that is related to texture, which is what we are normally interested in. And then lastly of those three, what's the relationship of soil texture and soil ECA? Let me see if somebody else can help me here. So, perhaps to facilitate our conversation, our thinking here, let's split soil texture into sand, silt, and clay. How do you think that soil electroconductivity changes across these three different soil texture classes?
It'd be higher like in clay because clay has a higher capacity of holding water
Yes.
than sand.
Yes, so that's really great. Thanks, Benedetta. So if we look here, this is an overall guideline for how conductivity changes as you change different soil textures. So really, sand has the least conductivity, and then silt is in between, and clay has the highest conductivity. If you remember, well, I'm assuming you all had at least one soils class. If you did not, then I'm sorry for assuming that. But if you remember, if you took a soils class and you remember, the reason why this happens is because clay is such a smaller particle size that has such a large surface area, and therefore it's a lot more reactive, right? So think of you applying fertilizer to a soil that is pure sand. Depending on the fertilizer, if you get a rainfall after you apply that fertilizer, you can lose a lot of that just by that water washing down the fertilizer. There is not a lot of charges in sand to keep hold of nutrients. Whereas in clay is the opposite. Clay is such a small soil particle, has such a large surface area and a lot of reaction sites that it just binds a lot more to any nutrient or salts in the soil. And therefore, this is that relationship, right? So the fact that clay has so many more reaction sites and so many more charges than sand is what makes clay, a texture of clay soil, to have a higher soil conductivity in this case. And this is the key. This is the reason why we use soil EC mapping tools like Various, because we want to run this through a field and be able to create zones of soil texture. And why do we do that? Well, soil texture is going to help us explain a lot of things about that field that we would only be able to learn if you were doing very fine soil sampling and sending them to a lab. So for example, soil texture is going to be related to water movement in that soil, to water logging capacity, to water holding capacity, to nutrient holding capacity, and cation exchange capacity, as you probably remember these terms from your soils courses. And so texture plays a really important role in determining yield potential in your field. And we're hoping that soil EC maps that we're creating through the use of Various, for example, are going to be related to soil texture, so we can understand what parts of the field are higher soil EC and therefore have a higher clay content, what parts of the field have a lower soil EC and perhaps less clay, more sand, or more silt. And I guess I just told you a lot of things that this slide is showing as text. So if you can assume that your soil EC map was collected under conditions that signal is mostly controlled by texture, soil texture, then we can use that map to understand zones of yield potential, for example. And this is very important in precision ag because as we just talked about, texture can be correlated with many yield limiting factors like water and nutrient availability and cation exchange capacity. So here's just one example of a field where on the left we have a soil electroconductivity map, and on the right we have an yield map. So for this field specifically, low EC areas are correlated with low yield areas as well. And then high EC areas are correlated with high yielding areas. Although these maps are not really great because we don't have a legend to know what color means what. We're just relying on the author's interpretation of what is low, what is high. But it's still showing us how that relationship is holding for this field. So for this specific field, low electroconductivity is connected to low yield areas, and high conductivity is connected to high yield areas. So now I have a quiz for you. So let me go to EOC and let me make it available for you. Just a second here. Almost there. Okay, I just made the quiz visible. Aman, can you confirm that to me, please? Okay, so the quiz is visible, and Luke, give me just a second here to make yours visible as well. But so once I make the quiz visible to you, Luke, then I'll give you all 5 minutes to complete it. But if you're already seeing it, you can go ahead and start. Okay, Luke, I think it's available for you as well, if you can confirm that.
Yes, it is. Thank you.
Okay, perfect. And I'll give you all 5 minutes here, and then we'll continue. All right, our 5 minutes are finished. Please go ahead and if you have not yet, please go ahead and submit your answers, and then we'll move on here. And really, I'm not like there is, I guess, a potentially right and wrong answer, but I'm not really looking for that. I'm just trying to see how you're thinking about this, given what we talked about today. All right. Let's see. All right, so I think everyone submitted. I was just checking at some of the answers here, and at least the ones I saw were really spot on. So overall, we do imagine that within a field, higher soil EC is going to be connected with more clay, which can be connected with better fertility, better water holding capacity, things that crops require to be high yielding. However, that's not always the case, right? So I think at least the cases I saw here, the answers I saw, you were pointing out, well, if it is too high because of salinity issues, then that's bad, right? That is not what we're looking for here. And that's exactly right. I want to give you one more example. So when I used to see more soil EC maps from the Midwest, where it's more common for you to have the first situation where higher EC is better. However, after coming here to Georgia, I started seeing a little bit of the opposite. And then, I started thinking about this, reading and talking to my colleagues. And then I realized that here in Georgia, it's very common for you to see high soil EC in a field being low yielding, and not necessarily because of salinity. The reason for that is soils that are eroded and they lose topsoil, and what remains is a very hard clay pen. So we see that a lot here in Georgia. I see that on my backyard. I have a part of my backyard that was eroded, and it's just so difficult to grow grass in that spot because it's so hard. There's so much clay that roots they have a hard time penetrating the hard pen. And this happens in farmers' fields as well. So you may see, if your research involves EOMonitor data and soil EC data, you may see fields that have high soil EC and very low yield. And that may be the reason, is because there's just so much clay that is so hard for plants to grow roots and penetrate that clay and really have a good crop stand on those parts of the field. So this is something that especially, in Georgia, we have our soils are more weathered than those in the Midwest. So we have, soils that are older. We also have more fields that are more sloped and therefore have been through a higher risk of erosion. And a lot of times we see those spots that the topsoil has been eroded. We're just left with a BT layer with a lot of clay, and very difficult for plants to cut through that clay or that clay layer. And so this is really, really common here in Georgia, where we see the opposite effect. High soil EC coming from those high clay spots, actually having a negative impact on yield, not because of salinity problems, but because of being so hard for roots to really penetrate and establish. All right, well, thanks for your thoughts on the quiz. And at this point here, we're going to move to the R component part of this exercise. But before I do that, I just want to open up and check if anyone has any questions about what we just talked. All right, I don't hear anything. So let's move to our exercise, our coding exercise. So I did just maybe 20 minutes or so before class, I sent you all an email asking for you to download the GitHub repo. I uploaded a new data set on the data folder and a new script on the class code folder that we're going to be using today. I asked you to create a new folder in your course folder. Let me come here to mine. So I asked you to create oops, wrong class. A 09_ soil EC. And then to create the code, data, and output subfolders to move the data into the data subfolder, the code into the code subfolder, and then to create an RStudio project. I still need to create the RStudio project on my side, so I'm going to be doing that. And if you're still catching up and doing this on your side, I also have a quick moment here to work on that as well. All right, so once we have that RStudio project created, let's just go under the code folder and then launch that script that we're going to be working with today. Okay, so the main goal of this exercise is to import soil EC data, and then we're going to again interpolate. So EC data is normally a point type of data, because even though this equipment is being dragged across the field, it is collecting EC data in a GPS coordinates and placing that in a spot on the field. And then it keeps collecting that and placing those points as it moves across that field. So when we bring into any programming language or any GIS, it's going to be a point vector file type. Because it is a point file type, we're going to have to interpolate. Also, we're gonna do interpolation because we want to keep the same grid as we've been interpolating everything else. So when it gets time for us to merge all these, they all match in space. And once we do that, well, we're going to interpolate for 2 depths. So this data was collected using a various equipment. So we have soil EC apparent electroconductivity at a shallow and a deep layer. So we're going to interpolate both of them separately and then export that data to files so we can use again when it comes time for management zone creation. All right, so I left you all the packages there. You should have all of them. So if you just hit play, it should go through without any problems. I left you there the My Theme Map object as well, which is just that those settings of a theme for the map that I've been using and creating for different, so all of our maps have the same theme, so we can call that as well. You know what? I think let me see here. Because either I have the wrong script or I sent you the wrong script. Because I think the one I have, even though it says partial, I think is the complete one. So let me make sure that's not the case. Okay, the one I sent you is the correct one. So I probably have an older version. Let me just delete mine, which is the complete version, so it wouldn't match what you have. This looks more like it. Okay, so the first thing, as always, let's import that data. So if you move the data set that I sent you, the soilec.csv, if you move that into the data folder of this project, then we're going to read it from there. we're gonna use the read underscore CSV function because it is a CSV file. And give it the quotation marks, // to get outside of the code folder. Then we navigate to the data folder and bring in that soil ec.csv. If you run that, you're gonna see that on our environment, and let's just print to take a quick look into it. So here we have about over 8,000 rows and 7 columns. As you can see, these columns were very poorly named. I'm not sure exactly if this was how we got out of the software that we extract SoilEC from, or if it was just how it somehow got to me this way. But as you can see, F1 through F5 are the columns that have our data. And perhaps we could guess what are those columns based on the values. But I would prefer not to have to guess a data set getting to you if it was not collected by you. Right, so I got this data set here from my colleague, Dr. George Velides, and he was able to tell me what were these columns. And so because of that, I know what they are, and then we can actually make sure we're working with the correct data when we start wrangling this. So this is the way that the data looks like. We're gonna do a few wrangling steps here. So one of them I already mentioned to you. One of the first things I want to do here is gonna be, well, first I want to apply clean names. That is very commonly the first step I always do in wrangling, because that helps me to code better when I'm doing the next wrangling steps. So I'm gonna do a clean names just to get everything on the same page as far as column names. Then we're gonna have to rename these columns. And I think until that point, I'm gonna show you and you're gonna code with me. But after that point, I will ask you what you think. All right, so let's go on ECAW, give it the assignment symbol. We're gonna start off with ECA dataset. Let's give it a pipe. Again, first thing I like to do is apply a clean names, just to make everything lowercase, easier to type. Now we could use either a dplyr select and rename while selecting, or we could use the function rename and just rename and don't select columns. Because there are some columns here that I really don't think we need, like FID and ID, and ID. I'm gonna use a dplyr select and select the ones I want to keep while renaming them inside the select already. So let's do a dplyr select. So first one, the F1 column is our X position variable. So X equals F1. So the way that we do here is so if we want to just select F1, we just say F1, right? We all are familiar with that. If I want to select and rename at the same time, I give the new name that I want, I give the equal sign, and then the current name that the dataset has. So I want to rename F1 to X while selecting that column. That's how you would do it. So X here is longitude. Y is going to be F2. So the column F2 has the latitude coordinates. F3 here is the electroconductivity apparent at the shallow soil layer, which at least on the documentation from Various, they assume shallow to be 0 to 30 centimeters. So I want to call this ECA 30 underscore DSM. So 30 because it's the depth, 0 to 30, and DSM because this is in decisiemens per meter. So this is going to be equals to F3. F4 is the deep layer EC. So what they consider to be deep layer is not 30 to 90, is actually 0 to 90. So the top layer is 0 to 30. The deep layer is not just 30 to 90, is actually 0 to 90. So I want to call this ECA 90 underscore DSM to be equals to F4. And then something that we can keep here, although we're not going to be necessarily using, but I just wanted to let you know, is that we also have elevation in feet as F5. So F5 is elevation in feet. So we can keep it 11 underscore FT for feet equals to F5. If we run that, then this is how the data looks like, a lot better, a lot more informative. All right, so what else do we need to do here? What would be your next step if you were faced with this data set?
How about plotting them?
Can you say that again?
Plotting. Can you visualize them by plot?
Yeah, so we're definitely gonna have to plot it, but I guess what I'm thinking more is like, what would be the next wrangling steps we still need to do here?
SF as ST.
Yes, ST as SF, right? So let's add a pipe SC as SF. We want to transform this data frame into an SF object, right? We need that when we're doing our interpolation. So here we're going to say chords equal to C function X comma Y. You've done this before, you're familiar with this. So if we run that and then we print what ECAW is, this is what it looks like. So it is a point, simple feature. What else? What do we need to do now?
CRS.
Yes, ST set CRS, right? So we need to determine what is the coordinate reference system that this was calculated as. So ST underscore set underscore CRS. And the value here, it's the EPSG code for WGS 84, which is 4326. So now this is simple feature of type points with the WGS 84 CRS. Okay, what about now? What else do we have to do? ST transform, right? So remember, every time you're doing distance-based operations, which we are doing here, interpolation is a distance-based operation. We want to have our layers in projected, so in meters and not in degrees. So let's do an ST transform. And then we're going to give here the CRS of 6345 for zone 16 north. That where this field is. All right, so now we have our point SF on a UTM zone 16 north CRS. Awesome. Okay, so this is pretty much what we have to do here on the wrangling side. And now, as Polly suggested, every time we make something, we should plot. So we should always visualize the result of what we did to make sure that things make sense and just to learn the patterns behind our data. So we can start right here with ECAW. My first goal here is going to be to plot the shallow electroconductivity, apparent electroconductivity. I'm going to start off here with a ggplot. Gonna add a plus. What geom do we need here, Mohit?
GeoMSF.
GeoMSF, right? Because this is an SF object. Thanks. So GeoMSF, I want to color those points according to, well, let me print ECAW here. So I want to color those points according to ECA 30 DSM. So we come here in GeoMSF, inside of AES, right? Because we're changing the color according to a column in the data set. I want to say color equals to ECA 30. You can run that and see how it looks like. This is how it looks like. I want to decrease the size of those points. So here inside of GeoMSF, but outside AES, we're going to say size equals 0.5. So we can kind of see the points a little bit better. You're seeing here, you can really see this pattern of, you know, each time the tractor or the RTV went over this field, it was one of these passes here, and it was collecting that data as it moved. So there's, you know, 8,000 points where each one of those points are one of those data that were collected on this field. As always, I want to change this to Viridis. So scale color Viridis B. I'm using B here for bins. So it creates bins of EC, as you're seeing right here. We could have used Viridis C if you wanted to give it a try, which does a continuous color scale. Perhaps in this case doesn't change as much, but I'm going to keep with B, but I just wanted to show you that C also works. B for bins, C for continuous. And then lastly, I want to apply our theme. So my theme underscore map is the one that we created. Oh. Okay. This is our shallow ECA map. So if we look at this, how would you interpret? So let me repeat that. So Amandeep here was saying, so darker color is low electroconductivity, yellow is high. So we have some spots of high electroconductivity, and this is shallow electroconductivity. Remember that on this part. And as we move, so we have on the right, we have more points that are lower electroconductivity as compared to the left side. Which I think we can also perhaps just create an intuition that this is something that perhaps we were expecting, right? So we know this field has some eroded sides. We know that yield is higher on the left or west side. So maybe in this case here, it makes sense that higher EC on the left is being connected with perhaps higher yield, like we saw on our yield data. All right, so let's repeat this, but for the deep EC, you can just go ahead and copy the previous or the code that we just developed. We're just going to paste below. But we have to change one thing. What do we need to change, Kiati?
I should change the color equal to ECA 90 DSM.
Perfect. That's exactly it. All right, so make sure you change your color to ECA 90 instead of 30 to look at the deep soil EC data. All right, so let me ask someone else. Luke, how would you interpret this plot?
Well, let's see. Just comparing with the previous one, it does look like our ECA is on average higher than it was at the shallower depth. It looks like our highest ECA are kind of in similar areas, sort of that that kind of diagonal of the yellow and the green from the northwest part, kind of going into the center and further south. And I would say it's on average lower conductivity in the eastern portion
Absolutely.
generally.
I agree with all of that. So Luke actually started with a really good point of comparing the deep EC with the shallow one. So the shallow, we see a range of values here from maybe 1 to 11, whereas on the deep, it goes from maybe, let's see, 2, no, this would be actually 0 here because it's 4 increments. So from 0 to 16 would be the range here. So the deep one has higher range, it's greater range, it has higher values compared to the shallow one. And also here on the deep EC, we see more of this separation between higher EC values on the west side or the left side of the plot, and then lower deep EC values on the east side or right side of the plot. Perfect. All right, so as we have already determined, this is point data. We want to interpolate because we want to have continuous data, but also because of the reason that we want our interpolated map to match the previous interpolated maps that we created for yield and soil terrain properties. As you know, the way that we're doing grids here is always by bringing the boundary and using the boundary as the starting point. So let's go ahead and bring our boundary. We're going to use readsf because the boundary is a .geojson file. And we're going to have to navigate to another project. So // to get outside of code, // to get outside of this project. Your boundary is on the 05 digitizing project. Under the output folder, you have a boundary.geojson right there. If you bring that here and you print it, you're going to realize that is in WGS84. Let's just go ahead and transform it, right? So we always want all of our layers that we're using here to have the same CRS. So we're going to transform to the CRS of 6345, which is that one that we've been using. So I noticed that we already spent here a little bit over an hour of class time, and I do want to be respectful of a break. So I think perhaps this is a good point for us to catch a 5-minute break if you want to stretch or do whatever. Let's do that. Take 5 for a break. And then once we're back, we're going to create the grid and then do the interpolation. So let me give you another 5 minutes here on the All right. Let's resume here. Okay, so we brought our boundary. Now the next step is going to be to create our grid. So as you may remember, so we're starting with our boundary, right? So we bring the boundary here. We're going to use a function. Let's see, does someone remember what's the name of the function we need here to create a grid? All right, Amandeep said st make grid. That's it. So in this function here, we have an argument for cell size, and we've been doing a cell size of 10. Remember that this number here is the same unit as the CRS of the incoming boundary. So our boundary has a CRS of which units are meters. So this is 10 meters. After we do that, we transform this to SF because it's not quite as an SF object. So ST as SF, we don't have to determine the coordinates because it already had a geometry column at that point. Now, if you remember, so we are creating a grid that is an SF object, but to interpolate, we need this grid as a raster. So here we're going to use a function st underscore rasterize. Oops, not Star Wars. Rasterize. Where again we have to say what are the dimensions of those cells. So dx, the dimension on the x-axis is 10, dy is 10 as well. And if you do this, and we just print or map using geom_stars now, because this is a stars object, we see that it's basically, I mean, right now it just looks like a big rectangle, right? But we do know that our field is here. The thing is that we have cells outside of the field that are also appearing here that we do not want them to show up. We want them to be set to NA because we don't want to extrapolate. We don't want to do interpolation outside of our boundary because we don't have data there. So with that, we have to crop. So we do an st crop using the boundary as our cookie cutter. So if we do that, and now you plot it again, we see our field sort of, as you remember, geom_star does not set the X and Y axis to the appropriate range as geom_sf does. So that's why it looks distorted, but this is our field. All right, so the first interpolation that we're going to do here is going to be for the shallow ECA on this next chunk. All right, this was a question on your exam, and I know not all of you got this right, but maybe this is the fourth time that we're doing this. What function do we need here? Gstat. Amandeep is sharp. Oh, you. So she's saying that she missed this question on the exam, so she made sure to go back and revisit this. Okay, so our formula here, if we just print the data, which is, where is our data name? So ECAW, right? That's where we have the data. So let me go back here, and I just want to print ECAW. So we want to first interpolate ECA30 DSM. So the way that we do that is we just say the column we want to interpolate, give it a tilde1, and then it has the data argument. So data equals ECAW. That's where that column is. If you run this and you print it, this basically, and I'm saying this again because I hope that you remember, the gstat function is just setting up what variable we want to interpolate and what data frame that is coming from. But the interpolation has not happened yet. Interpolation happens on the second step, which is going to be on this next chunk. So let me ask somebody online, what function do we need here to complete this interpolation? Marco, what do you think?
Predict.
Predict, right? So we call predict. We're gonna give this object that we just created above and then give our grid. So we're basically saying, take all these points that we established the formula here above and then predict them using IDW on the grid that is a raster grid. So if we do that, you're going to realize that it says inverse distance weight interpolation. And once that message fully shows up, then the interpolation was completed. If you have many more data points or more complex patterns, this predict can take maybe a little longer, but in our case, it was pretty fast. So if we just print this, the output of this, it is a stars object. It has the var1 pred, which is where our ECA shallow interpolated values are. Also has the var1 var that we already talked about this. The reason why it gives us that column and it's completed with NAs is because inverse distance weighted does not give us an indication of the variability around that interpolated value. That is something, however, that we do get from kriging. And we would do, so if we were running kriging, we would still run the gstat function and still run the predict. It's just that we would specify things a little bit differently. And because we're using the same functions, gstat and predict, to do IDW in kriging, then the author of this package and these functions just decided to give you var1 var always, regardless if you're using IDW or kriging. So we get it, but for us in IDW, it's all NAs. All right, so let's create a quick map here. So let's start calling a ggplot. If I want to show this object above ECA 30 IDW pred, what geom do we need? What do you think, Polly?
Geom SF.
Why do you think it's geom SF? So if you are
Oh,
on
it's geom stars.
geom stars, right?
I had to check the class for that object.
Yes, and that's exactly where I was going. So I'm asking these not because you have to memorize, because I mean you wouldn't, right? This is not the goal. The goal is just to test if you are all aware of, if you don't know, how would you find out, right? So if you come here, this is the object that we're trying to plot. If you just print it, it prints differently. So on the first panel, it says it is an stars object. So that would be one way. But also, if that's not clear, you can always ask for the class of that object, and that's going to give you the answer, right? So it's a geom stars, so we need, or I'm sorry, it's an object stars, so we need a geom stars to plot it. So we're going to say data equals to ECA 30 IDW pred. If we just run that and print this map, this is how it looks like. We are going to change a few things here. So Virides, scale Virides, scale fill Virides is what I was missing. And let's use the C for continuous. If we run that, now it looks like this. Now I want this map look more like the shape of our actual field. A couple of ways we can do that, but the one I want to do is to bring in the boundary. So the boundary is an SF object, and that's going to require geom_sf. We're going to say data equals boundary W. And I want to make sure that it has no fill so we can see through. So fill equals NA. All right, so when we bring GeoMSF, so the boundary is there, you may not be able to see because the line is very thin, but the boundary is there. And it's also GeoMSF fixes the issue with the axis not being in the correct way. I do want to do one more thing here, which is to change the label of this legend. To do that, we're gonna use the labs function. Because this legend is related to the fill, we're gonna say fill and then give a new name. I want to call this ECA 0.30 centimeters in DS per meter, in decisiemens per meter. If you run that and you print the map, what you're going to realize is that this legend name is kind of long. So I want to break line in a few parts here just to make it more concise and not occupy as much white space. And whenever you're using a string of text like this and you want to break line, you use /n. So I want to break line right before the 0 and again right before the parentheses ds per meter. So /n. When that prints, it basically breaks line for you. And then lastly, I want to bring here our theme. So my theme underscore map, just to make everything look the same or look similar. And this is what you should have. This is kind of interesting here because now perhaps on the interpolated map, we can see a little bit more clearly the pattern of having low, like a streak of low EC in the middle and kind of continuing to the east and then higher shallow EC on the on the left side, sorry, on the west side. Which again, if you remember, our yield pattern was kind of following this. We had higher yielding on the west side or left side, and lower yield on the east or right side. Okay, so let's do the interpolation now for the deep layer. So we're gonna basically do the same. We're gonna call the gstat function again. On the formula argument, we're gonna basically say ECA90 underscore DSM. That's the name of the column, ~1, and then say which data is this coming from. So this is coming from data equals ECA. Any questions in Tifton?
No.
Okay. So if we run it, again, we're just setting up that structure, but the interpolation has not happened yet. In our interpolation is a two-step process. So now if you come to the next chunk, we're going to use predict again. So we're going to predict this object above that we just created, ECA90 IDW mods, and give the same grid in raster format, which is grid underscore R. You run that, and then you print it. Again, this is a stars object. We get var1 pred with our interpolated deep EC in our var1 var full of NAs. All right, as always, we always want to plot things. So I left you here the plot for, or the code for the plot. I don't think you have to do anything because it's basically the same as the first code. We're just changing the column or the data set and also the label of fill. If we just run that and you print it, this is now our plot for ECA deep. And notice that ECA shallow is assumed to be from 0 to 30 centimeter depth. ECA deep is assumed to be from 0 to 90, not 30 to 90, 0 to 90. I also left you here the code for plotting it all together. Remember that, so it may not remember because I didn't focus on this, but on the beginning here of on the setup chunk where we load all the packages, we loaded here the package Patchwork. So this is the package that allows us to combine 2 or more plots into one view. Now, if I come back here to let's see, plotting it all together, you see that we have the 2 objects that we created for ECA shallow and deep, and they are connected by a plus. This plus specifically here is not coming from ggplot, it's coming from Patchwork. So if you run that, they would be side by side just like this. And then we just run the ggsave to get this figure exported to file. So if you come here on your output, you should have a soil ECA PNG right there with both maps and both legends. All right. So if you remember, the way that we've been handling this is, so right now, our interpolated values of ECA shallow and deep are in these stars objects. And these stars objects are raster. If you print any one of them, I'm going to print one of them here. This is how a stars object look like. You don't really see the data frame behind it. You just see some information about the file or the object itself. In contrast, SF objects do give you a view of the data frame. And I think they're better for visualizing, multiple layers of data, which in our case, those multiple layers of data are actually just different columns, right? And they're all connected to the same polygons when we transform this from raster to vector. So I'm calling this grid extraction, which basically is just transforming that raster interpolated ECA shallow and deep to SF, to vector. So let's do first here for the shallow one. So we're going to start off with the object that has the raster interpolated shallow, which is ECA 30 underscore IDW underscore pred. Now, to transform this from raster to vector, from stars to SF, we're going to use ST as SF. We do not have to give coordinates because it already has that information, but we do have to change a couple of arguments. One of them is S points equals to false. So it transforms those raster cells into vector polygons instead of vector points. We don't want points. And then we also say merge equals false, another argument we want to change here. If you run this and you print it, now at least I have 3,848 rows because these are the number of polygons I have in my field. You have a different value on your side, again, because our boundaries are different. But this is the number that we've been seeing, or that I've been seeing with the other layers as well. Whatever number is on your side, it should be the same number you've been seeing with the other layers, like the terrain and the yield that we've already worked with. One last thing here is I just want to select var1 pred and rename it to something more informative. So let's go ahead and use a dplyr select, where I want to call this ECA 30 underscore DSM equals to var1 pred. All right, so we just did this for the shallow one. Now I want to go ahead and do for the deep one. And I already left you the code just to highlight it for you. A couple of differences, here is that the incoming data set, the incoming raster is different, right? Is the one for the deep layer rather than the shallow layer that we just did above. And then I'm renaming var1 pred to ECA 90 DSM instead of 30, right? That makes sense. We just want to make sure we know which layers we're talking about. So as we do that, we have the same number of rows. Now we have this ECA 90 DSM column in this object. Now our next step here is going to be to merge both of these layers and finally to export the merged single layer to file. to merge here, so merging two SF objects. Let me get started with the code. So let's begin with the ECA 30V, which is the one that we created here. So this object was ECA 30V, the one that we got the raster one and transformed to SF and selected and renamed. That was ECA 30V. So we're starting off with that. Let's give it a pipe. What function do we need here to merge ECA 30V with ECA 90V? ST join, right? That's correct. Thanks, Aman. So ST join is the function. We're using ST join because we're joining two spatial data sets. Where you may remember that we have used in the past left join, which is also a join, but instead of relying on the spatial position, it relies on two columns having the same name. In this case here, we're joining based on the spatial position, so we're using ST join. So we give here ECA 90 underscore V as our incoming or second data set that we want to join to the first one, which is ECA 30. We want to change the join type. We want to join to be equal to ST equals, just the word, don't add the parentheses. And finally, we want to say left equals true. That's what we want to do here. So if you run that and you print ECAV, it still has the same number of rows, 3,848, but now it has two fields, one for ECA 30, one for ECA 90. So now we merge both of these into the same file. And again, finally, we get to the end of this exercise where now we're going to export this layer to file. What function do we need here? Let me ask somebody online. Marco, what do you think?
Write JSON.
Close. So there's,
SF.
yes, write SF, exactly. That was a good guess, though. I don't think that function exists, at least not in SF package, but that was a good guess. So write SF, right? Because it is an SF object. So we give the object name, ECA underscore V, and then we give the path. And remember that the path is actually the path, the file name, and the file extension, all in that string, right? So we want to get outside of code. Let's go inside of data. Let's call this ECA underscore V dot GeoJSON. So notice we give the path, ECAV is the file name, .geojson is the file extension. And then, as always, you're probably tired of hearing me say this, we need to change that delete DSN to be equals to true. So delete underscore DSN equals true to make sure that if you by mistake run this line of code more than once, that you don't end up with twice as many rows. You get the same number of rows because it's not appending, it's overwriting. If you run that and you check your data folder, you should have ECAV there at this point. Okay, so an overall summary of this exercise. We imported the vector soil ECA data, which in fact, when we imported, it was just a CSV. It was not a vector geospatial file at that point. We transformed that to, we did some wrangling, and part of the wrangling was to transform it to geospatial. We then interpolated soil apparent electroconductivity at 2 different depths to the same grid that we've been using for the other layers. So they all overlap each other. They all match each other spatially. And then after doing the interpolation, the output of that is a raster, and we are transforming everything to vector just to make it easier for us to visualize them. So then we transform them into vector. We join both the shallow and the deep depths into one object and then exported that to file. All right, so we're getting close here to run management zone creation. So the next exercise is actually going to be that. So just a quick recap here. If you remember, we had yield data from 3 years. Each one of those years we wrangled. We did the yield editor by filtering some points out, and finally we interpolated. And then with the interpolated yield map of each year, we derived the spatial temporal stability classes of unstable, high stable, medium stable, and low stable. After that, we brought in the terrain exercise where we use elevation data. So elevation data came in as a point. We interpolated the elevation data. And then once it was a raster, we could calculate other secondary terrain properties of, we did slope, aspect, and flow direction. We bundled all that together, exported to file. Finally, today, we brought in soil EC data, right? So we brought soil EC at 2 depths, processed, interpolated, combined them, saved to file. Now on the next exercise, we're gonna bring back some of these process layers, interpolated and process layers, into the same script, into the same exercise, where we're gonna do management zone creation by using a clustering algorithm. So that's what's gonna come next. Also, something just to point out here is, let's say if this is a field that you're working with and you have more data, perhaps you have gridded soil data that you would like to bring in, clean, interpolate, export to file, and then bring in when you're creating zones. You could do that, right? Or we could even use remote sensing data. We could use satellite imagery as one of our input layers for creating management zones. We could have done that. We're not going to do it, at least not. We're not going to use satellite remote sensing data yet, but we will after we finish with the management zone creation and validation. So anyways, I think the overall message I'm trying to say is any other geospatial layer that you think could be related to EO potential that you have, you could bring that in as well, process, interpolate, export to file, and then bring that back when we do management zones, right? This workflow here applies to every other geospatial layer that you could bring for this field, not just soil EC, terrain, and yield, right? It could be others. So just wanted for you to keep that in mind. The more layers you have, you're just gonna add more workflows here to process them. And then when time comes, you just bring all of them for creating management zones. All right, I think that's all I had for today. We still have 10 more minutes here. So make sure you save your script. I'm going to open attendance on GitHub so you can claim your attendance. All right, I just opened the issue on GitHub. Make sure you claim your attendance. And if you don't have any questions or if you don't want to follow up in anything, then you're dismissed. But I'm going to stick around for 5 minutes or so in case anyone has any questions for me.